Essential RL, TD Lambda Learning. Deploying TD Lambda. Credit assignment is an essential problem in RL. In RL, the agent receives delayed rewards from many actions over many time steps. How do you assign credit for the various actions? Some methods for helping with the credit assignment problem are Monte Carlo updates, TD methods, value functions, eligibility traces, and end-step updates. Monte Carlo updates are full episode returns where the agent learns from experience. These typically have high variance and no bias like reinforce. Assigning credit can be hard since every action/state in the episode is judged on the return. A poor action or bad state may still get some credit for a good result due to a later action. TD updates, like the TD0 method we covered in Section 1, allow bootstrapping incomplete episodes. However, TD0 only looks one step ahead, which can be inefficient. End-step returns allow multi-step returns and bootstrapping over multiple steps. The TD target can look n steps into the future. End-step methods relate Monte Carlo to TD methods as being on the same spectrum. TD lambda is a way of weighting n-step returns and relating Monte Carlo and TD methods. TD0, i.e. lambda equal to 0, is the one-step return. TD1, i.e. lambda equal to 1, is the Monte Carlo return. The image on the slide shows a hypothetical weighting for different n-step returns decayed by lambda n-step returns, represented by G. Eligibility traces are a way of unifying TD and MC methods and implementing them online. The traces are a method of dealing with the credit assignment problem and what the lambda and TD lambda signifies. There are many different ways of formulating the eligibility trace. We used TD lambda in Section 3 when we called the A2C loss functions. Calling TD lambda on its own is similar to TD learning from Section 1. We set up tensors for state value, reward, discount, and a bootstrap value. Lambda is an optional argument that defaults to 1. We can set lambda from 0 to 1 or input a tensor of lambda values. T is the time sequence of the tensors, where index 0 is the first time step of the tensor. B is the batch size. Note that bootstrap is a single value for each batch. We'll see an example of reshaping the input to the T by B tensors in the code. The code example in this section uses the temporal differences return, which is the difference between the discounted returns and state values. This is also used in the truffle actor critic functions in Section 3. The code for this video will be using TD lambda to play Frozen Lake. Frozen Lake is a grid world-like 2D environment. The agent tries to navigate to the goal while avoiding holes which end the episode. Actions taken are non-deterministic, i.e., if the agent tries to move right, the agent will fail to move right some of the time. Also included is a simple toy example to allow you to try different values of lambda and other hyperparameters and see the effects. Let's look at some code. This is a toy example to let you see how changing different hyperparameters can change the lambda returns. This also shows simple usage of TD lambda. We set up the tensors, input them into truffle.td lambda, and run the truffle tensor in the session. This is similar to how we did TD learning in Section 1. We'll use Frozen Lake for some of the videos in this section. We render a few states of Frozen Lake here, showing how the agent moves in a 2D world, starting in the upper left and trying to reach the goal in the lower right. The start state S, the goal right, and the holes H, which end the episode if the agent falls into them. The agent doesn't always move in the direction the agent intends to. Sometimes an action fails and the agent moves in a different direction. We set up the truffle tensor as before and run it in the session. Lambda defaults to 1. Truffle lets us customize its lambda functions. We can either enter in a constant value for lambda or a tensor of lambda values. In this example, we use a constant lambda. Optionally, you can do a lambda placeholder. And then in the session, you would feed that lambda placeholder with different lambda values. Here's running the truffle lambda tensor in the session. Note how we reshape the values. We don't use the loss output in this example. Instead, we're using the temporal difference output and using that to update the tabular estimates. So these are the state value estimates, and we use the TD lambda temporal differences to update the state values. Further resources.